Let's now take a look at an example. So we're told we have a homogeneous dielectric with relative permittivity 2.5, which fills region 1, x less than 0, while region 2, x greater than 0, is free space. So we're given an expression for our electric flux density d1 in region 1. So that's equal to 12 in the x direction, minus 10 in the y direction, plus 4 in the z direction, nanocoulombs per square meter. And what we want to find is two things. We want to find our d2, our electric flux density in free space in region 2, and theta 2, the angle d2 makes with a line normal to the interface. So as always, what I think we should do with these types of problems is go ahead and sort of sketch out a rough drawing of what we're dealing with. Now, because we have x equals 0 as sort of our boundary, of course this is going to be a plane, but in terms of looking at the angles and drawing, it's going to be a little easier to look at in 2 dimensions. So I'm going to draw this in 2 dimensions and kind of describe how you can consider it in 3 dimensions to sort of visualize it a little more accurately. So we've got our x and y. So here's our x. And so let's say that this line here, of course, if we have this center, this is going to be our x equals 0. So this is our boundary. All right, so over here on the right side is our region 2. So this is our free space with relative permittivity of 1. And over here on the left side, this is our region 1, where we have a relative permittivity of 2.5. And so looking at our equation, we see in D1 we have 12 u of x minus 10 u of y. So again, let's just sort of draw this roughly. So we see it's going to be going to the right in x and down in y. So we have something that looks like this. Again, just roughly for our D1. Now what we need to consider is we also have this z component. So if we say that positive z is coming out of the page, then our z is sort of, our line D1, as we move from our left to the right, is sort of coming up out of the page towards us. So what we're going to want to do, of course, is decompose this into normal and tangential components. So we can say we also have some D1 tangential and some D1 normal. So this is going to be D1 sub t, and this is going to be D1 normal. Now our normal vector is going to be, as we're going to see, just an x component. So that's going to be sort of at this peak. Well, let me see if I can describe this a little better. So we're going to have sort of this is going to be at some z value, so sort of at the highest point, and then our d1t and our d1 are sort of going down back into the page to a lower z value, the lowest point of which is over here at this vertex or vertice on the top. Okay, so again, sort of a little complicated drawing this in 2D and trying to visualize it in 3D, but hopefully that makes sense. If not, let me know and we can sort of try to discuss a little further. So now what we're saying is we have some D2 over here in region 2. So I'm going to draw it down here. So let me see if I can make that line a little straighter. So we have something that looks like this. So this is our D2. And again, we can talk about this in terms of a tangential and a normal component, so we can make sort of a right triangle there. So we have D2 tangential and D2 normal. And so what we're interested in with that theta 2 is, let's switch over here and get a dashed line. We want the angle between our D2 and some line normal to the interface. So we're interested in this theta 2 right here. And so again, from geometry, we can determine that that theta 2 is the same as this theta 2 inside our right triangle. And so for something later, I'm going to go ahead and define this as theta 1. All right, so that was sort of a lot of work just to set that up. But again, I think that sort of getting a rough visualization of the problem is a good way to start. So now what we want to do is we want to take a closer look at that D1 expression. So let me go ahead and copy that and pull this down here. And what we're going to do is we're going to sort of break it apart into its normal and tangential components. Okay, so what we can say is, let's sort of rewrite this and say we have, explicitly, we have d is equal to 12 times our u of x plus negative 10 u of y plus 4u of z. And so the reason I've sort of grouped that up is, of course, we have here, this is going to be our normal component, d1n, and this is going to be our tangential component, d1t. And so with that in mind, it might be easier now to go back to that triangle over here and sort of visualize how that's changing in terms of z as well, adding that third dimension. So what we can say is let's assume a charge-free interstate, and that's a reasonable assumption because we have a dielectric. So unlike a metal, remember, charge isn't going to move to the surface when we apply an electric field. It's going to be bound surface or bound volume charge. So unless we add some external charge, it's fair to assume that we have a charge-free interface. And so we're not told anything about that explicitly in the problem. And so what that means is that our rho s is going to be 0. And ultimately, we can say our d2 normal is equal to d1 normal. And so in this case, that is going to be our 12 u of x. All right, and so the units of that were nanocoulombs per square meter. So ultimately, though, we want to figure out our total d2, and we know that d2 in general is equal to our normal component plus the tangential component. And we already know our tangential component, so we've got this one. Now we just need to figure out, or we've got our normal component, now we just need to figure out our tangential component. And we can't say anything, our electric flux density is discontinuous at the interface, or our tangential component is. So what we need to do is we need to consider our electric field component that's tangential to the interface. So let's come down here and say we know that our E sub t is continuous across the interface. And so what we can do then is we can get an expression for our E1 based on our D1. So we can say E of 1t is equal to E of 2t. And of course we don't know E of t1, but we can say, well, that's just equal to D of 1t divided by our epsilon 1. And similarly, we can just change the E2, or we can rewrite it in terms of our electric flux density, so D of 2t divided by epsilon 2. And now ultimately we're looking for this D2t, so let's rearrange that and say D of 2t is equal to epsilon 2 over epsilon 1 times D of 1t. Now, of course, each of those epsilons are going to have an epsilon naught term, so ultimately what that's going to do is they're going to cancel out, and we'll have epsilon R2, so the relative permittivity of region 2, relative permittivity of region 1, times our tangential component of 1. And in this case, we have free space in region 2, so that's a relative permittivity of 1. And in region 1, we have 2.5. And we're multiplying that by our tangential part of DIT, or D1t. So we have negative 10 in our y direction, plus 4 in our z direction. So we sort of just multiply that out, and we get that D2t is equal to negative 4 in our y direction, plus 1.6 in our z direction, and again, our units are nanocoulombs per square meter. So now we're going to put these two pieces of information together, so we know our normal component and our tangential component, and we have this relationship here. So what we can say is we can say we have our overall D2 is then equal to 12 in the x direction minus 4 in our y direction plus 1.6 in our z direction. And that's nanocoulombs per square meter. Okay, so there's the answer to the first thing we're looking for. And again, let's keep in mind that this first part here is our normal component. So this is, let's just say this is our normal. And then the second part, our y and z components together, is our tangential component. Okay, so now the second thing we were looking for was that theta 2 angle. So the angle between the normal, a line normal to the interface, and our D2. But really we said we can just focus on that triangle. So let's go ahead and do that. So let's redraw sort of that triangle here. See if I can get it to draw me a nice triangle. There we go. So we've got a right triangle there. We know this angle here is theta 2, and this distance we know is 12, and then our tangential component, the length of that is going to be the square root of 4 squared plus 1.6 squared. So that's just taking the magnitude of this tangential component here. And so what we can say then is that our tangent of theta 2 is equal to that square root of 4 squared plus 1.6 squared divided by 12. And so if we solve that for theta 2, we get that it is approximately 19.749 degrees. So now we've answered everything that the problem asked for, but I want to take this a step further and just say we could do similar analysis. We could draw a triangle for region 1, and what we could find is that in region 1, so for region 1, we would find that theta 1 is about 41.909 degrees. And the reason I wanted to point that out is that we can then use the relationship we talked about before of refraction at an interface, and we could say, as expected, if we plug in all these values, we have that tan theta 1 over tan theta 2 is equal to the ratios of our dielectric constants. So epsilon R1 divided by epsilon R2. So that works out as expected. And so what that tells us is that if we had been given theta 1, we could have plugged directly into that equation instead of going through the geometry. Or maybe, as we did here, we could just use that as sort of a double check. If you want some more examples, if you want some more practice with examples dealing with these boundary conditions, these interfaces, you can look on pages 204 to 207, and that'll give you some extra practice. As always, if you're having issues or questions while you're working through that, let me know. This is the last video in this unit. There are a couple other small sections at the end of the chapter that I want to at least bring to your attention, even though we don't have enough time to cover them. The first is a small section that deals with high dielectric constant materials. So let's see if I can spell that correctly. So high dielectric constant materials. And you'll also hear these referred to a lot as just high K materials. And so one application area of these is electronics. So this has really helped a lot with miniaturization of electronics. So not to go into too much detail, but basically as we shrink and get smaller, we want ways to miniaturize that oxide, but we don't want to miniaturize it too much, otherwise it becomes conducting, it breaks down really easily. So having a higher dielectric constant allows us to maintain a large enough oxide thickness while still shrinking other dimensions of our transistors, for instance. One other interesting application area or interesting section at the end of the chapter is dealing with graphene. And so graphene is, of course, a very conductive material with very unique properties, so that's something interesting to look into as well. And then the final section, again, very brief, is piezoelectrics. So with any of these, if you're interested, I definitely encourage you to read through those. They're not very lengthy sections, so it could just be sort of a starting point to look into other items if these are topics that are of interest to you.